Hey everybody, so I've been working backwards through the Advent of Code challenge years and doing all the previous year's puzzles, which I've never done before. And I've got a little library of tools and techniques which I kind of want to show off. So I'm actually going to show you a problem I've already done and how I might start it. So this one's about counting IP addresses basically. So IP addresses are 32 bits. So the first IP address, well, in the range is 0, and the last one is 2 to the 32 minus 1. Those are 32-bit integers. And they're typically expressed in dot decimal notation with 1 byte per segment. So here, yeah, it shows the range. This is about 4 billion. So what they've given us is a file with ranges that they want to omit. And the first part of the problem is what is the lowest valued IP that is not blocked. So this is kind of late in the year, so these problems tend to be a little bit more difficult. The early ones are very simple usually. So what I usually do is I have a directory where I have a directory per day. And so I just make a directory. So this is day 20. And I'm just using tmux here. And I have a little helper script called get input. And what that does is it uses my cookie and it gets the it just essentially curls the input for that day into a file for me, and then also copies my stub base script to this directory if it doesn't exist. And it just gets the year and the day based on the current directory names. So I just basically run that script, and that sets me up. And then in here I can edit that file. So this is my base script. I have some very common imports, this little debug thing, so I can either wrap a print in debug and turn it on and off with a command line switch, or I can use this Boolean switch to sort of omit blocks from printing. I have a little function which parses the input, so I read, just basically read lines from standard in. I found this to be the most convenient thing. I can put command line options very simply using sysargv, and I can specify files using sysstandardin. So basically I just I iterate the lines and I strip new lines in white space for the beginning end. This is just a very common sort of transformation. And so by default, part 1 just prints whatever's in the data, whatever's in data. So I have a little macro here which it watches for changes in this file, clears the screen, and then runs parts 1 and 2 using the input, the default name for the input file. And so we can look at the input. You'll see it's just an integer and an integer separated by a dash. So if I just run my watcher script, and this will not exit, it just keeps watching, and it will rerun the script if the script changes. So very simply, I'm just going to make a list line and then iterate through the lines and split them. Let's see, line, let's do int under for under in line dot split on dash. That should give us 2. And then we're going to do blocks.append a tuple AB. Typically use, then we'll just return blocks. So we typically use immutable types where it's convenient. And then in part 1 we have blocks. And then let's say block in blocks, print block. So kind of step 0 is, okay, can we parse the input? And you'll see now I have a tuple of the different values in here. And that's kind of like the first step. then you sort of, I flip back between, the problem and the program as I need to sort of figure out the puzzle, so to speak. But I think for this particular video, I'm going to skip all that. So I saved my previous attempt at this here. So if you look at that one, you'll see I've cleaned up some of the imports I didn't need. The input parsing is about the same. And essentially, like, there's a bunch of sort of overlapping ranges in the input data. So what I've done in the very first part of the problem that wants you to find the first available IP is I've merged all those ranges. So I just have a little function here. So I say while we merge something, and then immediately set that to false. So if we don't merge anything in a subsequent loop, then this will exit. And then basically I walk through the list comparing. So I sort, and I remove any. Here there would be null things in the list if I've done a merge. I removed those and sorted the list. So now I should have so A and B, as I'm comparing adjacent things in the list, if they overlap, I can merge them. And this is just sort of a shortcut. Like if one of the pairs is none, then I just continue through the loop and I go to the next pair. And essentially what I do is I start to compare the values in the list, so or the values in the tuples. So if this is essentially saying if B is fully encapsulated by A, then we can just remove B. And I just mark that as none. B is blocks I plus 1. And I modify the list so I can say merged true. That will make me run through the loop again. Because I may now need to merge A with whatever the next thing in the list is in the next iteration. Else, if that doesn't match, if the first element of B is between A0 and A1, then they overlap. So essentially I replace A with the new thing, so the new range A0 to B1, and I mark B as deleted. And also in this case I've merged something. So this will essentially run until there's no items that overlap. You could go another step further now that I'm thinking about it, because a lot of the ranges have the last value and the first value of the next item. They're just one apart, so they actually essentially fully encompass that range. But for this problem, I haven't done that. I've essentially just skip. There's no IPs there to be counted, so when I calculate that, I get 0. So once I have them merged, it's fairly easy to compute what the solutions are. So the first part is I do the similar thing. I loop through the blocks and I say if B0 minus A1 is greater than 1, that's like the first IP, because blocks will be sorted at the end of all this. So I just print that and I can break out of this loop. So that's the first number here, whatever that is. That's almost 24 million. And then the second part of the question is how many IPs are there? So at the start of the range, between 0 and the first block, there are this many that many IPs at the beginning of the range, which I think it's 0 actually. Here I can just print blocks 0. And you'll see the first block starts with 0, so that means there's essentially no IPs there, but that may not be the case in everyone's input. And then I basically spin through the blocks in the same way, and I say okay, what's the difference between them? And also the range is inclusive, so you need to subtract 1 here for this to come out right. So essentially for every pair of blocks, I count the IPs that are available in between them. That may be 0 in some cases, or a lot of cases. And then at the very end of the range, I need to count how many IPs are between the end of the last block and 2 to the 32 minus 1, which is the last IP. So you'll see in this case there, so this is 967,000, and this is 900, wait, I guess there's 0 there as well. 294, yeah. I thought there was in this problem there was some at the end of the range, but there's not. But again, may not be the case for everyone's input. But for my input, there's 125 IPs available between all the ranges of blocks, and I think the number of blocks goes between. So if we at the top of the function, we can say how many blocks are there. Len blocks, and at the end of this merge step, len blocks again. So you'll see we go from like 1,100 blocks to 179. So there's quite a lot of duplication and overlap. So that's essentially the entire problem solved. Those are the two answers. I didn't use any of the debug stuff. For some of these problems, it's just not really needed. So I can actually, if I wanted to, I could delete this as well since it's not used. And that's the whole thing. I like to, at the end of the day, just run it time and see, how much time my program's taking. This was a fairly simple one, not involving a lot of computation. So that's it. So then I just git add this. I add a description to the README for this year. This is kind of useful if I want to go back. It's greppable in the repo, so if I encounter a problem that's very similar to a previous problem I remember, I can grep through and sometimes find the other problem. I'm in 2016 now, so I've done quite a lot of these, but sometimes I can steal code or something from other years. And then I just get, let's see if I am. 2016, day 20. Whoops. And that's it. I think one other interesting thing is I have a little library of stuff. If you go to lib, in particular, I've got some algorithms. I think that just includes a cycle finder. Graph includes like breadth-first search and Dijkstra, and they're slightly different flavors. Breadth-first search comes up all the time because shortest paths happen all the time. Int code was from like I think 2018 or 2019. A lot of the problems that year use this little computer assembly language thing. And these grid things actually come up all the time. Grid.py, it comes up in probably like 30% of the problems. And this just includes a lot of really repetitive, like 2D array grid type processing code. And there's essentially two classes. There's a grid class, which uses like a list of lists to represent the 2D array. And there's a sparse grid which uses a dictionary, so not all the cells in the array are stored. Sparse grid is handy if you don't know the size, whatever you're working with, because like the print function will just compute how what the range of values is in the grid and just print what is sort of in the dictionary. Grid is handy if you know like the exact sizes, and you'll see like sparse grid inherits from grid, so they share the same type of interface, but there's some properties for like the box enclosing, the size, x and y sizes, if you want to iterate over the x values, if you want to iterate over the y values of the points, if you want to get the value of a point, get the character that represents a point, and also set and set C, removing stuff, adding stuff, moving. I haven't used move a whole lot, but you can essentially move points around. You can clear the grid, and then there's various neighbor functions. So neighbors 8 includes the diagonals, neighbors 4 does not, just like left and right, up and down. Neighbors 4 diagonal now, so that includes only the diagonals. Step returns a new point in a certain direction. I never really use these set. This is always sort of under development. I copy this grid class into any problem that uses it because I don't want to have to go back and fix broken stuff if I change the class. And then these transformations have come up from time to time. So like this class saves me so much time when I use it because it handles all the little. You can see how like just ugly some of this code looks, but it handles all the sort of little edge cases. So you can take a grid, flip it X, flip it Y, or rotate it 90 degrees in each direction. Very handy. Same thing for the like grid class versus sparse grid. You can hash the grid, so if you need to store it in a set or dict, or sometimes it's handy if you're doing like some sort of search where you need to figure out if you visited a certain state. I recently implemented like slicing, so you can slice a little square or line out of the grid, and then you can modify it and place it somewhere else. So I think that will come up again. And yeah, these are the generic versions of the functions which do all the stepping and whatever. You can see just like kind of ugly code. So it's very handy to be able to just like pull that out of lib and use it when needed. Let's see. Let's look at something. So look, 18 used grid. What was this problem? I think this one, yeah, this was a generative sort of grid. So they give you the first line, and then there's rules. So the next row looks at the values from the previous row, and then you generate this, and then you compute, how many. The carets are unsafe squares, and the dots are safe squares. So in this case, there's 2005 safe squares, and then what was the second part? Part two. Oh, part two is a much larger grid. So sometimes this works. You can just, I think part one there's 40 rows, and part two there's 400,000. So if you've done something sort of ugly in part one, sometimes you can't reuse it because in part two the value will be too big for it to run in time. But I think in my case, it takes just like 10 seconds to run or something. There you go. So in the 400,000 line version, and I think there's algorithmically like this pattern will just repeat after a while, which I'm sure is like the fast way to do this. But if something runs in 10 seconds, you just sort of like, it's good enough. These are essentially throwaway problems. Yeah, I'm sure if you printed more lines, you could probably even see the pattern because you can sort of see these diamonds in here. So yeah, that runs in like 9 seconds, so that's fine. But you can see like the grid class is there was a lot of code in the grid class. There's not very much code in this. I essentially just import the grid. I take the first row of the input which they give you, that thing, pass it into the grid, and then I pass all zeros for however many lines there are, rows there are. And these are the values that get stored in the array, in the lists inside. So then I iterate through the y's. If y is 0, I skip it because it's already been given, and then I iterate through the x's and I compute whatever the thing is. And here I set, this is me getting the values of the previous row. And then if those match this pattern, then I set that value in the current row. And then the counting is just pretty easy. So that's a flavor of a lot of the grid problems. Sometimes you need to do like breadth first search and stuff. I think maybe actually 13. Yeah, 13 is actually that flavor. You'll see there's some function that computes what the grid is. You generate the grid, and then I write a little neighbors function, so I can walk on any square that's 0 as a next point, and then I BFS. So you're trying to get from point 11 to point 3139, and the first part is just to print the distance, and in part 2 they want to know how many points are within 50 steps. So you see, again, like fairly complicated, but I'm also leveraging from graph breadth first search. And that is this little function, BFS. So frontier neighbors is a function, and you can optionally give it an endpoint. And this is just implementing sort of like canonical depth first search in Python. I have some more work to do on this, but I sort of develop these things along the way as I need them. So this is like quite a lot of problems use grid, and then, you know, it's fairly common. It's fairly common to see, you know, you need to search a grid, or you need to or you need to find shortest path inside of a grid. So it's pretty useful to have these sort of built-in, baked-in things in my little library here. So like BFS and grid is pretty easy. All right, I think that's all I have to show you guys. Thanks for riding along. You'll see I submitted my answers the first time I ran through this, and for 2016 I'm getting pretty close, and I only have 2015 left. I want to get to 400 stars and then start working on some other things. But this has been a really fun set of puzzles to go through over the holidays and early part of the year here.